What's going on, everybody? Welcome back to my YouTube channel. It's Max, and also welcome to 2022. So today we're going to continue our video series on creating our crypto app, and this is kind of where we left off. We built this encryption tab. We could encrypt and decrypt messages, and we could also change these settings to change how the encryption and decryption worked. And I mentioned we were going to talk about this key exchange tab in the next video. And so today we're going to talk about what this tab is and why we want to have it. So first, let's just imagine how two people might use this application. So like any encryption example, we're going to have two characters, Alice and Bob, and we're just going to imagine them using this application to talk to each other. So let's say we have Alice, and this notepad over here is sort of going to represent like a messaging app, and then Alice will have this top version of the application, and Bob will have this bottom version. So Alice might say something like hey, hey Bob, are you there? Bob might go, yeah, I'm here. Alice might say, what settings should we use for encryption? And then Bob might say, let's use R1 equals like 22, R2 equals say 33, and R3 say equals 7 or something. Okay, so then both Alice and Bob would set their application to these settings by just typing in those values into the corresponding fields. 22, 33, and 7. And from here, now all their messages that they exchange can be encrypted. So Alice might start off the encrypted conversation by saying something like, hey, what movie do you want to see tonight? And then encrypt that text. And so this is what Alice will send to Bob. Bob then receives this encrypted text and sees the message. And so he might say something like, I was thinking of seeing the new Spider-Man. So he'll encrypt that. Alice will get that message, and then she might say something like, oh, cool, I have been waiting to see that. See you at 7 p.m. And then Bob gets that. And now he knows that him and Alice will be seeing Spider-Man at 7 p.m. And he might just say, actually, wait, which message did I last send? This was, oh, so this is what Alice says. And then Bob might say, cool. Whoops. Bob might say, cool, see you then. So here's a simple example of two people using this application to secretly send messages talking about what movie they want to see and when they want to see it. However, there's two big issues with this setup. So one of the assumptions there always is in cryptography is that the channel you're sending messages over isn't secure. So the assumption is that someone can eavesdrop on this channel and see everything that's getting sent. So the two issues are that even though this might look like jumbled up stuff that only Bob and Alice can decipher, actually, if this channel isn't secure, this is a lot easier to decipher than you might think, for two main reasons. The first reason is that the settings of the application aren't encrypted at all. So if anyone can read this conversation, they can read the settings perfectly fine. The second thing, and really the most important thing, is that this application is not secure at all. And we know the application itself isn't secure because, one, you're watching a video series on how to make it, and two, in the comment section of that video series, I'm posting a link to the source code on how to make this app. So if anyone has, the know-how on how to eavesdrop on your application, they can probably figure out that, what kind of application you're using to encrypt your text, and they can probably find their way to that application if it's publicly available, and then they can use the non-encrypted settings to just type into their version of the application and then just decode everything in your conversation. So now that we know the security flaws with this setup, we can start talking about the key exchange. And what the key exchange is a feature of this application that allows Alice and Bob to secretly send these three application settings to each other in a way that the person eavesdropping on their conversation can't access. So what this key that they're going to be exchanging is basically some secret number that has these three settings encoded in it. So like we mentioned earlier, with any cryptography example, there's always going to be at least two characters trying to talk to each other, usually named Alice and Bob. And in this case, there's going to be a third character named Eve, who's going to be eavesdropping off the insecure channel that Alice and Bob are going to try to communicate through. So the first step that either Alice or Bob can initiate, it doesn't matter, is for one of them to compute two numbers. One's going to be called the modulus, and we're going to call that P, and the other is going to be called the base, which we'll denote as G. In this case, we'll have Alice create P and G and send that to Bob. And since she sent it to Bob, Eve also sees it as well. Next, Alice and Bob are going to create what we call their private keys. And we're just going to denote these as lowercase a for Alice and lowercase b for Bob. And here we'll also denote that orange text represents information that's considered private and thus not sent over the insecure channel. And green text is public, and it will get sent over the insecure channel, and Eve will be able to see it. Next, Alice is going to compute her public key, which we're going to call capital A, by computing G to her private key mod P and send that to Bob. Next, Bob is going to compute his public key by computing G to his private key mod P and send that to Alice. Next, Alice is going to compute Bob's public key raised to her private key mod P, and then likewise, Bob is going to compute Alice's public key raised to his private key mod P. Now, both Alice and Bob come to a shared secret value that Eve doesn't have access to. And we can see that if you expand what Bob and Alice's public keys are, basically the math reduces to both of them are computing the base G to the power of B times A mod P. So now S is a shared secret key that both Bob and Alice have access to that Eve doesn't have and has no easy way to compute with the information she's received over the insecure channel. The process we just went over is known as the Diffie-Hellman key exchange and is a very famous protocol in cryptography. And while this implementation isn't really used much anymore, more sophisticated versions of the Diffie-Hellman key exchange are used all over the place on the internet in more modern cryptography applications. So with that said, the next thing to ask ourselves is, what kind of security does this protocol have? How secure is this shared secret value S? And can Eve figure out S with the information she has of Bob and Alice's shared public keys and the public modulus and base? And actually, the problem of figuring out S based on with these four pieces of information is known as the Diffie-Hellman problem itself. And the question is, can Eve figure out what S is from this? Currently, the easiest way we know how to solve the Diffie-Hellman problem is to solve another very hard problem called the discrete logarithm problem. And what the discrete logarithm problem is instead of Eve trying to directly solve what S is using the information she has, she's going to try and solve for either Alice's or Bob's private key by trying to solve one of these equations for X and Y respectively. And the reason this is called the discrete logarithm problem is because it's discrete because we're doing modular arithmetic, and it's a log because we're trying to solve for something in the exponent. And this is also a very hard problem because there's no closed form solution to solve either one of these equations. We can't just do some math and then end up with something like x equals, some nice formula here. Basically the only way to solve for x and y is to brute force try basically every value for x between 0 and p. And so if p is some, small number, like, I don't know, like 100, like a computer could very quickly, brute force through this and solve the discrete logarithm problem and thus solve the Diffie-Hellman problem, and you could figure out the shared secret. But in practice, these values like p, this modulus, instead of being some number like 100, it's some massive number that's like hundreds of digits long. So long that if you try to brute force solve this problem, it's going to take your computer like years to do or something like that. That's really where the security of the Diffie-Hellman key exchange is baked into. It's really baked into this discrete log problem and how hard it is to brute force solve this equation. And also how you can always add more security to this by just increasing the value of p, thus increasing the search space that Eve has to brute force her way through. All right, I think that's probably enough for this video today, but just as a quick recap, today we talked about some of the security vulnerabilities that the application currently has and why we need a key exchange. And then we talked about what the Diffie-Hellman key exchange was. And lastly, we talked about some of the security behind the Diffie-Hellman key exchange and how secure it is. And so yeah, I think we'll just leave that here. And the next video, we'll start actually coding up the Diffie-Hellman key exchange in that second tab. Thank you all for watching, and I'll see you guys next time. Bye.